So I apologize. Yesterday I did not do a good job explaining why everything was happening. So we have a centrifugal fan that's trying to sling the air. It's pulling the air in from the sides, and then it's slinging that air outward with centrifugal force. That's what that blower wheel is doing. When we have an airflow restriction, that means we're able to sling or move less quantity of air, less CFM of air. And we need to think that air has weight to it. So every cubic foot of air has weight. So when I'm moving less cubic feet of air, I'm moving less weight. I'm doing less work. So we have an airflow restriction. We can move less boxes, less cubes of air through this fan. Because we're moving less cubes of air, we're moving less weight of air. That's less work on the motor. That's less work that the motor is doing. Now, why does the amps draw? And that's exciting. So to understand what's happening with the amperage of this motor, we have to realize that there are two separate sets of windings. We have the run winding, which we'll talk about first, but we also separately have the start winding, or the auxiliary winding that's helping that motor run. We're going to separate those. We're going to talk about the run winding first. So inside of here, there's going to be a set of primary windings. We're going to have a coil of wire, a coil of wire, a coil of wire, a coil of wire, and a coil of wire. As that energy is running through there, it's creating electromagnetism. And because it's alternating current, we end up with electromagnetism moving around. And that on the stator, that magnetic field moving on the stator, is causing the rotor to turn. And even though this rotor is made of aluminum, we're able to induce a magnetic field into that rotor to make it work like a magnet. So we're able to make energy by making that rotor turn. Now we have to think about resistance. The electricity, if we actually ohm out this motor, we're going to see that there's very little resistance on the motor itself, on the windings itself. So if we were to ohm it out, very low resistance. If you were to apply Ohm's law to that, you would see, wow, it should be pulling a whole lot more amps. And when the motor first starts, it does. It pulls a whole lot of amperage until we get this motor turning and we get that magnetic field induced into the rotor and get that rotor turning. Once this rotor starts turning, that magnetic field is pushing back. It's creating extra resistance, pushing back against the windings, which is pushing back against the flow of electrons. Let me visualize this for you. So here I have some magnets. You can see that they're sticking to the metal. They are just magnetic balls. Here we have PVC and have copper with a little bit of PVC taped to it just so that it wouldn't affect the metal on the stand. So when we energize that motor, that run winding, the electricity is just flowing through there straight through. It's just the resistance of the wire, which is almost no resistance whatsoever. But once we induce a magnetic field into that rotor and that rotor starts turning, we end up creating electrical resistance. And that resistance increases the ohms. It slows down the amp flow. Let's compare it side by side. So even though the copper and the aluminum is not magnetic, it still responds to the electrons that are sitting there. When we push a magnet through, it's trying to push those electrons separate, which is Lenz's law. And it's really cool science that's happening inside of there. When we first energize this motor, there's very little resistance. It's just the resistance of the wire. But once we make a magnetic field, we induce a magnetic field into the rotor. This part, then we make it become a magnet. Now, as this is turning, that magnetic field is acting against the magnetic field of the coils here. So what's happening is, as this motor is getting up to speed, it's increasing the resistance against what's happening on the windings itself. And so it's cool because now we're having a harder time pushing electrons through there because there's a lot more electrical resistance. So it's pretty cool seeing that balance. Now, the other thing we have to talk about is the difference between synchronous speed and actual speed. And the difference between those two is what we call slip. So as this motor is running, we have a synchronous speed where we can actually count the number of poles. We can do a calculation and find out how fast the RPM of the magnetic field is turning. Now, the motor itself will be turning slower than that because of the load that's on it, and the difference in those is the slip. So what we have to think about is how that load is going to be affecting what's happening inside this motor. So when we don't have any resistance airflow-wise, we're moving a whole lot of CFM, which means we're moving a lot of weight of air, which means there's a whole lot of ultimate resistance against this wheel. So that means there's a big difference between the slip that we're having and the synchronous speed of the motor. So we're going to end up with less resistance and more amperage. So that means amperage can flow through this motor faster until we get that balance that it needs. Now, as we start blocking the airflow down, this motor has what we call more and more slip of the wheel. Not the motor, but the wheel will have more slip because it can't move as much air. There's no place for the air to go. So it just kind of spins. It slips in the air. Well, because there's no place for this air to go, this doesn't have as much load on it, which means the RPM of the rotor itself will then go faster. It will increase. Now the RPM of the rotor is closer to the synchronous speed, which means we have more electrical resistance, which means our amperage actually drops down. And when we block the airflow altogether, this is just sitting here free spinning. It's not moving any work at all. So our rotor is really close to the synchronous speed, which means we have the max amount of resistance between the magnets in here, which means we have the least amount of amperage flowing through the motor itself on the run winding. So that's kind of how that balance is working. But that's just the run winding side of it. Oh, and we can actually go back. If you have a multi-speed motor and you're just bench testing it and you're actually to check the RPMs, you'll see that no matter which speed tap you use with no load on it, they all have the exact same RPM. These speeds aren't true speeds. It's just different speeds make the motor weaker that controls how much slippage there is. So that's a story for another day. Now let's talk about the start winding. The start winding or auxiliary winding is to assist the motor, to make the motor more energy efficient. But now we have a separate set of windings that split between the run windings all the way around. So 1/60th of a second, we actually send electricity through this windings, and that electricity is helping that motor turn. But then as it's alternating current, 1/60th of a second later, we have a magnet that's flowing through a magnetic field, which is essentially a generator that pushes electrons back through the same wire. And if we actually look at something like this, if I have this example and I take the magnet off and spin this, absolutely nothing happens. No matter which way we go, nothing at all happens. But when I put the magnet on here, we can see that now we're actually generating electricity. So this is an example of putting a coil of wire through a magnetic field, and the motor's just doing the opposite. We're sending a magnetic field through a coil of windings. So we're actually becoming a generator. So it's increasing or adding to the voltage that we already had. We had 115 volts coming in. Now we've added to that 1/6 of a second, and it's creating that voltage, that back EMF that's pushing into that capacitor. And that voltage is going to change with the RPM. So if we have a little bit of voltage on here, right, we're turning slow, there's very little voltage. That extra voltage pushing into the capacitor is low. But as it turns a whole lot faster, we create more voltage. So as we end up with our motor moving less air, there's more air slippage on here. That means our RPM of the motor itself gets closer to the synchronous speed. In other words, it's turning a lot faster. And because the motor's turning faster, we end up pushing more electrons back through the start winding onto our capacitor. And because we have a higher voltage, which is electrical pressure, electromotive force, back EMF, we're able to push or stack more electrons on one plate. So then because we're pushing more electrons on this plate, then 1/6 of a second later, all those same electrons go back through this winding into the motor to help the motor turn. So because our RPM is going faster in the motor, we're increasing the back EMF because it's turning faster. We're pushing more pressure, more voltage, more pressure, pushing more electrons onto that plate. Then 1/6 of a second later, it's flowing back out. So that's why we have that very small increase in amperage, because we have an increase in the voltage. So it's all tied in together. The back EMF, the back electricity, all this works together. Now, it's not an issue on the capacitor if our capacitor is rated for 440. It's blocking the airflow entirely close. We got 420 volts maximum, and it's a 440 capacitor. Now, if it was a 370 capacitor, then yes, it could damage that capacitor. But if it's a 440, no. And 1 amp difference isn't going to change a difference. And next, we're going to do a video using a thermal imager showing the difference in heat that that motor itself is not causing damage to the capacitor. But hopefully this helps explain how all that connects together. I do have to give a shout out to Roman Baugh, who was explaining about why the voltage increased. I didn't fully understand it. He explained it to me about this motor turning faster, creates more voltage, and that's why the voltage increased across that run capacitor. Hopefully that helps. Never stop learning. Have a great day.